Very good morning. Yesterday we were looking into some of the derivation related to the macro scale heat transfer, a closed system conduction, and also the convective heat transfer transport equations. And then we also looked into the constitutive relationships which are required to close the relation between the heat flux and the temperature. So, we have once again revised or revisited these constitutive relations in conduction, convection and radiation. I think most of you are quite familiar with them, and as I told you that for example, the Fourier's law, whatever that is stated as a constitutive relationship as a hypothesis originally by Fourier, can be actually shown to derive from the microscale principles. Now, we will also continue with some more constitutive relations. For example, in fluid mechanics, okay, the most commonly used constitutive relation is your Newton's law of viscosity. So, this is also called the Newton shear stress law. So, what it says that is for a Newtonian fluid, you can relate your shear stress, maybe it could be tau xx, tau xy. So, it is a shear stress, that stress is a tensor. Okay. So, in 2D you have basically 4 quantities of stress, in 3D it is 9 elements. So, anyway you can relate for example, shear stress with the corresponding strain rate, right, that is your du by dy through constant of proportionality, which is your dynamic viscosity. So, this is valid for so called Newtonian fluids which follow this particular behavior, right, and this is another example of a constitutive relationship which is required to solve the Navier-Stokes equation, because once again when we write down the momentum equations, we have everything in terms of stresses, and in order to solve them we need this closure problem. So, closure problem for closing, we need this particular constitutive relationship given by the Newton's shear stress law. So, this is again another one. So, what is the unit of the dynamic viscosity here? In terms of SI units kg per meter second, in terms of newtons, how do you write it? Newtons second per meter square. Okay. So, this is your relationship that you are very familiar with in fluid mechanics. In mass transfer, okay, we are not probably exposed to too much of mass transfer in our department, but chemical engineering, they are very often concerned with mass transfer as important as heat transfer. So, in case of mass transfer, what is the constitutive relationship? Fixed law of diffusion. So, therefore, you see that this is not a problem only that we have in heat transfer. So, every domain has a closure problem and a corresponding constitutive relationship required to close this. So, the fixed law of diffusion, now we can draw an analogy from your heat transfer and state an equivalent law of diffusion, constitutive relationship between the mass flux and your, what is the corresponding variable instead of temperature? Concentration. So, we will have mass flux, let us denote this as J, okay, double prime, distinguish this from heat flux Q double prime, corresponding concentration gradient or species gradient. So, this is dm by dx. So, instead of temperature gradient, you are replacing this with your concentration or mass fraction gradient. Okay. And then you have to use the corresponding diffusivities. In case of the Fourier's law, you use the thermal conductivity, and now you should use the diffusivity, mass diffusivity multiplied by rho, so that it is dimensionally consistent with your. So, here your d is in terms of meter square per second. So, this is your diffusivity, mass diffusivity. This is equivalent to your thermal diffusivity alpha, that also has the units of meter square per second. Okay. So, this is your fixed law of diffusion and also very important closure required for the mass transport problems. We will also take one example in electrical engineering. Okay. So, that is your Ohm's law. So, how do we state write the Ohm's law? You can draw an analogy between from heat transfer, mass transfer and apply the same thing for Ohm's law. So, now instead of Q or J, what do we have? Current density. Okay. So, let us use the notation again JC for current density or current density flux, okay, double prime, and what is the equivalent quantity to which it is related, just like temperature, mass fraction, voltage. Can we put it more fundamentally? Electrostatic potential difference. Okay. So, you have the gradient of electrostatic potential. So, we will say d phi by dx, okay, and you have to again put a minus sign because the current flows from a higher potential to lower potential. So, the gradient will be negative. So, in order to make sure the current flow is positive from higher to lower, there should be a minus sign, and the relationship between these two with a proportionality. Okay. What is the proportionality constant here? So, in case of heat transfer used thermal conductivity, now we should use electrical conductivity. Okay. So, sometimes we use the notation sigma for electrical conductivity. Okay. Resistivity is 1 over this. So, but we will use in terms of conductivity. So, see you the way that we have defined all these constitutive relations, they all look analogous, right. So, some flux quantity as a function of some gradient of the fundamental driving potential. Okay. In the case of fluid transport, it is the velocity gradient. Okay. In terms of current, it is the electrostatic potential gradient. In terms of heat transfer, temperature gradient. Mass transfer, you have the concentration gradient. Okay. So, this is how they are all related, and once again the units of the current density is in ampere per meter square. It is like a flux quantity. Thermal conductivity is an ohm inverse meter inverse. So, this is in terms of phi, this is your electrostatic potential. Okay. So, therefore, we have looked at some of the classical constitutive relations generally applied for the macro scale transport equations required to close the governing equations and solve them. Now, we also saw the similarities or analogies between these different constitutive relations, and the next question that comes out is, are these equations applicable at even small scales? So, generally people tend to state these equations without stating that the continuum approximation and where the validity of these constitutive relations are held. But you should understand that once you go to nanoscales, as we saw defined by the Knudsen number, high Knudsen numbers, you cannot once again use these constitutive relations as it is. In fact, when we do this derivation from the microscale or nanoscale limits, we get these equations at the condition that your Knudsen number is small. Okay, that is the limiting condition under which we can derive these constitutive relations from the Boltzmann transport equation. Okay. So, now the next thing I think all of you to understand is to do a simple scaling. So, I would call this as a scaling analysis or scaling trend or whatever you want to call it, to understand the importance of the ratio of the relative surface to volume forces. Okay. So, now if you take the case of a sphere, so you have a sphere of radius r, and if you want to calculate the ratio of volume to the surface area of the sphere, so what will be this particular ratio? 4 by 3 pi r cube, 4 pi r square, r by 3. So, therefore, so as your r keeps reducing, the corresponding volume to the surface will also keep dropping, or in other words your forces. Now, if you look in terms of forces, now let us take an example of a surface force, a volumetric force, and calculate the ratio of those two. So, for example, if you take the volumetric force, gravity is a classical example of a volumetric force which acts on the entire body. Okay. So, let us take the ratio of gravitational force, and what is a good example of a surface force? So, assume this sphere is some kind of a drop or a bubble, and outside you have ambient. So, let us say this is your bubble and you have a liquid ambient. So, naturally there are two phases here, and therefore, there will be a surface tension which will be balancing the pressure difference across that interface. Okay. So, therefore, we can now write surface force as surface tension force here. So, how do you calculate the gravitational force? You have rho times gravitational acceleration times the volume of the sphere. So, you have 4 by 3 pi r cube divided by, what about the surface tension force? The surface tension is acting along this perimeter, whatever you are looking at. So, the surface tension is defined in terms of Newton per meter. So, you are just looking at the surface area. So, here when you are talking about, so you can associate 2 pi r, because the units of sigma is what? Newton per meter, not Newton per meter square. So, it is associated with just the perimeter circumference. So, therefore, the ratio of this will lead to 2 rho g r square by 3 sigma, right. So, now you can, I will give you two values. One, take the case of radius r equal to 1 meter. So, let us say this is a big bubble in an ambient liquid. I will give you the property, let us say rho is 10 power 3 kg per meter cube and sigma is 78 into 10 power minus 3 Newton per meter. Okay. So, you do this for two values of radii, one is r equal to 1 meter, calculate this ratio. So, let us say that this ratio is some gamma. Okay. So, calculate this ratio gamma for r equal to 1 meter and then reduce the size to 1 millimeter. Okay. From 1 meter you reduce the size to 1 millimeter, calculate the value of gamma. So, what will be the result for 1 meter drop bubble? So, let us say 8.4 approximately into 10 power 4, right, and what about 1 millimeter? So, that is 8.4 into 10 power minus 2. So, therefore, reducing the size of the drop from 1 meter to 1 millimeters. Okay. So, that is 3 orders of magnitude we have brought down. The volumetric force, the ratio of the order of magnitude of volumetric force to the surface force has come down by what, 6 orders of magnitude. Okay. So, therefore, if you are looking at a bubble of 1 meters, there definitely gravity is very important compared to the surface tension force, and therefore, not only for the bubble drop problem. So, if you take two phase flows in also mini channels, micro channels, and then you look at the flow pattern in a big channel, you will find that in the big channel gravity is playing a very important role in the flow patterns. Now, when you go to channel of a millimeter size, the gravity is relatively unimportant compared to surface tension, and you will find the flow patterns are dominated by surface tension force. So, this is a very good example where you have to know what are the importance of relative importance of forces. Sometimes when we write down the Navier-Stokes equation, we tend to neglect certain forces without knowing the scaling trend. So, this is a good example to show you that that certain forces become suddenly very important at different length scales. Okay. So, what we will now do, so far we have looked at continuum till now, we will go into the little bit into the micro scale nature of the energy carriers responsible for the macro scale transport. Okay. So, very briefly I will call this as microscopic picture of energy carriers. So, why we are doing this? Because first we looked at continuum, and then we looked at transport of heat, we looked at transport of mass, and then we also looked at say transport of current and so on. Now, what is responsible for this transport? So, that can be understood only into when you zoom in into the molecular picture, microscopic picture. Okay. So, if you take for example heat conduction. So, we talked about the Fourier, we derived the governing equation for heat conduction and also the closure using the Fourier's constitutive law. But what is happening essentially at the micro scale is that, so if you take a system or a slab where only conduction is happening, or it is a box which consists of gas, okay, where only conduction is assumed to happen, you have a high temperature T hot on one end and you have T cold on the other end, and this is filled with gas molecules, okay, plenty of them. This is at still macro scale where continuum approximations are valid. So, when you talk about heat conduction here, what is essentially happening? The average kinetic energy of the molecules on the hot side is increasing, okay, when you heat the gas on the left side, and they therefore, the collision average collisions are also increasing on the left hand side, and gradually these collisions are transferring the energy from the hot side to the cold side. Okay. So, this is what is happening at the micro scale, and you look at the micro scale picture, it looks a little bit more straightforward, but when we write the equation in the macro scale, we assume that there is a diffusion, right. So, this collective collision and transfer of energy is approximated as a diffusion process, and we relate your heat flux or heat transfer rate to the gradient in temperature and so on. So, this is how we bring out so many approximations, but at the micro scale it is essentially simply collision and transfer of energy from one molecule to the other. Okay. So, now if you are talking about therefore different media you have different energy carriers. If you are talking about liquids and gases, so you are talking about essentially molecules which are responsible for this conduction process. So, if you are talking about dielectric solids or semiconductors, so which you can assume as insulators or semiconductors. Okay. So, most of the crystals fall under this category. So, in this case the lattice vibrations are responsible for heat conduction, because you do not have any media like gas or liquid filling. So, what is responsible for heat conduction, and you do not have too many free electrons in the case of semiconductors or dielectrics. So, only the lattice vibration should be responsible for heat transport, and you should understand that these lattice vibrations travel at the speed of sound in the lattice. So, that is the maximum speed at which they travel, right. So, these can be described with representing them as particles called phonons. Okay. So, as the name suggests, you are talking about sound, phone, from the root, Greek root. So, that means it is something to do with the acoustic speed of propagation of these lattice waves, which are responsible for the heat conduction, and the corresponding particles which travel at this speed. So, they are called phonons. Okay. So, these are virtual particles, that means they are massless, and you cannot really dig into a crystal structure and look for a phonon somewhere. Okay. They are just our imagination. So, really there is only a lattice vibration, but we associate them with this kind of phonons, just like photons. Okay. If you put a microscope and try to zoom in, you do not find particles in light. Okay. So, they are just a way of understanding, because they seem to behave, and nobody knows how these particles look like, what is the mass of this. So, they are called virtual particles, whereas electrons are physically observed, right. You can actually observe in an atomic structure electrons. So, they are real particles. Okay. So, therefore, if you look at the lattice structure, so how do they know? How do you see the lattice structure? So, you have these atoms in a particular solid. Okay. You know, I have represented this lattice structure by means of these atoms spaced. Why I am doing this way is that these atoms cannot come too close and then just simply sit on top of each other. So, there is a certain forces acting between these two atoms, which is holding this particular crystal structure. Okay. You have different structures, FCC structure, BCC structure. So, why this is coming is that the interatomic potential is basically resulting in the appearance of this lattice structure. Okay. So, if you are therefore looking at the picture of a semiconductor, so you have these atoms, okay, and you also have what? Somewhere free electrons. So, somewhere from these atoms some electron has been knocked out. The chances are of finding more free electrons in semiconductor are very minimal. So, you will find maybe somewhere 1 or 2 free electrons floating around. So, they are also responsible for conduction of heat. So, if you look at metal, In the case of metal, what happens? You have abundance of conduction band electrons. So, they are all free electrons and they are primarily responsible for heat transport. So, therefore, in case of metals, so it is basically the electrons which are responsible for heat conduction. Okay. So, if you therefore measure the thermal conductivity of a semiconductor device, semiconductor element and metallic element, you will find the huge difference is because of the contribution of electrons in metal and phonons in a semiconductor device. Okay. So, therefore, depending on the media, you have different energy carriers, right. If you are talking about the thermal radiation, okay, we talked about conduction now. So, if you go towards thermal radiation, so thermal radiation on the other hand is a result of the excitation of the electromagnetic waves. Right. So, this is the oscillation of these electromagnetic waves, particularly in the bandwidth which is radiated by the sun. So, which is starting from all the way from UV, visible, infrared and long wavelength infrared. Okay. So, all this together falls under the thermal radiation band. So, our visible spectrum is very limited. You have 0.4 to 0.7 micrometer band, 400 to 700 nanometers is a visible band, and that is also the band over which the intensity of the black body intensity of the sun, if you say a temperature of around 5000 Kelvin, that is where it peaks, okay, and that is where our eyes are also tuned to observe in the visible wavelength. Okay. So, that is where the sun's intensity is also peaking. So, the nature has devised in such a way that our eyes can tune into seeing objects because the sun is emitting the maximum intensity in that particular wavelength band. Okay. So, whereas to look into the UV or IR you need special devices, right, and what are the energy carriers associated? Now, these are again waves. So, therefore, to describe the equivalent particles, virtual particles, we use photons. Okay. So, these have got very interesting history, I am not going to go over them. So, over a period of time they have evolved different models, okay, understanding first as particles, then correction to waves, and then finally Einstein comes and says no, they are both waves and particles. Okay. So, and then that all the not only the electromagnetic waves, but any wave, we are talking about electrons, we are talking about phonons. Okay. So, any wave, that is what we will see in quantum mechanics. So, we can always fundamentally in the quantum level they are all waves, okay, and at a larger picture you can use the wave particle duality, use the particle base, because classical mechanics can be applied to particles, Newtonian mechanics. So, that is easier to solve for us, okay, whereas the waves require solving Schrodinger's equation, which is computationally very intensive and sometimes unnecessary also, right. So, therefore, you have different energy carriers considering the different media. Now, when you are looking at this lattice structure and the force potential between the different atoms, you can actually plot the interaction potential between two atoms. So, you have two atoms, you can actually imagine these two atoms to be separated by means of a spring. This is a very simple picture that people usually represent. So, the atoms are usually approximated as a spring mass system. Okay. The interaction potential, so if they come too close together, the spring is going to push them out. Okay. If they are too far away, the spring is going to get compressed. So, this potential is usually used when people do what is called molecular dynamics. So, or they are looking at fundamentally only molecules and they are solving for the forces of interaction between these molecules. Okay. So, this is the most basic potential that is used. So, what happens? So, let us say the potential on the positive y axis is positive potential, negative y axis is negative potential. So, positive potential means it is attractive, negative means it is repulsive. Okay. So, we can actually, for the sake of convenience, we will reverse this. So, we will put the negative on the top and then positive on the bottom. So, the repulsion will be plotted on the positive part of the y axis. So, when you are plotting this as a function of the spacing between the atoms, okay, when the spacing is extremely small, you have a very strong repulsion. Okay, the repulsive potential is negative and I am plotting this like this. Now, as your radii, the separation between the two atoms increases, you will find that somewhere they are stable and just standing there. Okay. And as you keep increasing this, what happens? You have an attraction potential which is coming out. So, this will transition towards the positive potential. So, that is your attraction potential. Okay. And then that will continue and then it will just reach some asymptotic value. Okay. So, this part of the repulsive potential is described by the curve which is like this and then it goes to an asymptotic value. So, this is given by a constant by r to the power 12. Okay. This is your repulsive potential. Okay. The attractive potential is defined by a curve which is b by r to the power 6. This is your attractive potential. So, this is the behavior of these two curves is generally approximated. So, the overall potential, interatomic potential, so therefore, at r going to infinity, this tends to go to 0 asymptotically, right. So, the overall potential between the two atoms is generally written as A by r power 12 minus B by r power 6. So, this is the standard form of what we call as Lennard-Jones potential. It is a very common potential used in molecular dynamic simulations. So, fundamentally you are looking at a big system of molecules and you are just solving F is equal to ma, right. So, and that force is represented by this potential here. Okay. So, this spring mass system, if you are applying it to that entire lattice structure that we have shown. So, we just showed these atoms hanging in space, but for the sake of looking at the mechanics of them, you can assume that they are like connected by a spring mass system which is holding them together at some equilibrium, and that is forming the crystal structure. Okay. So, if they are disturbed from this, so they will tend to resist that disturbance and try to come back to this equilibrium state. So, you can basically draw this spring mass between all of these atoms and they look something like this. The equivalent, now you see when you are applying a higher temperature to the left compared to the right, essentially what is happening. So, the vibration due to this spring constant, the spring constant now will become a function of temperature, it is actually a function of temperature. So, the vibration of this atom spring mass system here on the left end will be higher than on the right end. Okay, so this will propagate as waves through the crystal. Okay, essentially the vibration of these atoms are propagating as waves which travel at the speed of sound within this lattice structure, and that is responsible for transport of heat. Now, the equivalent way when you are representing this as a particle called phonons is to represent this system with cloud of phonons, phonon cloud. So, all these are some kind of molecular representation of gases. Okay, this entire system is now represented by particles, virtual particles of phonons. Okay, so you have two pictures. One, you have vibration waves, lattice vibration waves transporting heat. The other picture is collision of phonons. This is your particle picture, right. So, you can treat this as phonon gas, just like you are treating gas molecules and you are talking about collision and transport of energy from the hot side to the cold side. So, you can look at both pictures. Okay, we can derive the corresponding thermal conductivity and so on, looking at both the pictures, and still you will get reasonable match agreement between the two. Okay. So, therefore, now you see the analogy, we can talk about molecules in gases and liquids, and in case of solids phonons, okay, which can also be treated like molecules in a box. So, instead you replace the gas molecules with phonon gas, understand, and similarly in metals electron gas. Okay. And when you are talking about thermal radiation, you have, or any electromagnetic radiation, you have equivalent picture of photon gas. So, all these are like particle pictures. Okay. So, we will look into each of them in detail. So, I will give you a kind of summary. So, between the different energy carriers. So, this will be a little bit comprehensive, so that you can understand some more details apart from the role in heat conduction. So, I will call this as basic characteristics of energy carriers. Okay, so just I want to define certain constants that we will be universal constants that we will be using. So, let me define the Planck's constant H. This is 6.6262 into 10 power minus 34 joules second. Okay, this is your Planck's constant. Very frequently we will also be using what is called as a modified Planck's constant, denoted like this, H cross. This is nothing but H by 2 pi, and this is 1.0546 into 10 power minus 34 joule second. We will also be using the Boltzmann constant K subscript B, 1.38 into 10 power minus 23 joules per Kelvin. So, these are the standard universal constant we will be using in this particular course very often. So, that is why I am giving that upfront. So, let us go to the characteristics. So, I will have different columns here, attributes. So, first for phonon, electron, then we have molecules, and what else? Photons. So, all the energy carriers that we know. Okay. So, these what are the attributes? First we will define source, where do they originate from? So, what about phonon? So, lattice vibration. Electrons from the nuclei. So, they are basically freed from nucleus. Okay, these are free electrons here. Okay. So, free from nucleic bonding, right. Molecules are molecules in a medium, liquid or gas, right. So, these are atoms, and photons, yeah. So, you can say electromagnetic vibration or oscillation. Right. So, these are electromagnetic waves which are oscillating, described by your sinusoidal equation and so on. So, this is your source. Now, let us look at the next attribute, propagation media. What about phonons? So, typically the propagation media is solids, it could be also metals. Okay. So, but the most dominant ones are in semiconductors, dielectrics, and to a lesser extent in metals. So, electrons, and you have molecules, liquids or gases. And what about photons? You do not need actually a medium for transport. So, either in vacuum or in any participating media. Okay. And then the third attribute, I will call this as, although I have not introduced them, but nevertheless we will just briefly state that here, energy presentation or energy representation. So, how do we represent the energy of phonons is usually by using the momentum, okay, or through the frequency. So, we will use that, we use what is called as wave vector, denoted by the notation k. So, the momentum is actually related to the wave vector, we will see that. Okay. So, that is nothing but the modified Planck's constant times the wave vector will be the actual momentum. We can also relate the energy to this, and we can also write this in terms of frequency. So, now you see, although we are calling this as particles, we are, when we look at the energy, we can represent the energy looking at the wave picture. So, because wave vector can be attributed only to a wave, similarly with the frequencies, right. So, apart from that, the phonons have what are called as modes, different modes we will see what are those modes in the future. Classification of phonons, you can have acoustic modes, we have optical modes, we have longitudinal, transverse. So, these are all the waves, again the waves which have to be represented into particle nature. Okay. So, modes and polarizations, because if you talk about waves, again electromagnetic waves or any waves, you have polarization, direction becomes important, right. Now, similarly, if you look at electrons, we can also describe this using wave vector, okay, and also a specific property called spin, which is unique to electrons, okay, based on the Pauli's exclusion principle. So, we will again come back to that. Now, if you go to the molecules, we are primarily talking about momentum of these gas molecules, momentum p, and then we are also talking about kinetic potential energies of these molecules. Okay. For the photons, similar to the phonons, you have the wave vector, or you can also write in terms of frequency, okay, and also polarization. Electromagnetic waves definitely will have polarization, the energy will depend on the polarization. Okay, one more last this thing today for today before we will continue this tomorrow. So, this is basically your particle type. Okay, this we will do when we work with statistical thermodynamics, but right now it is good to have an understanding what they represent. So, when you talk about phonons, they are represented by the equilibrium distribution function called the Bose-Einstein distribution function, and therefore, these kind of particles come under the category of bosons. Okay. Same with your photon as well. The photon is also described by the Bose-Einstein equilibrium distribution function, and they are also category of bosons. Okay. So, what is the nature of these kind of particles, bosons? So, you have what is called as indistinguishable particles. So, they all look very similar, alike, and you cannot distinguish them, okay, and also any number of these particles can occupy a given quantum state. So, when we do quantum mechanics, now you will understand what is this quantum state. After that, when we do statistical thermodynamics, you will see how the particles can be distributed into these quantum states. So, the particular feature of these kind of bosons, either photons and phonons, are these. So, they are essentially indistinguishable particles, and therefore, you can put any number of these particles in a given energy state. Okay. So, they are the primary characteristics of bosons. Now, apart from that, now when you talk about electrons, what is the distribution function? Fermi-Dirac. So, therefore, these are also called fermions. Okay. So, in the case of Fermi-Dirac distribution function, the characteristic is that these particles are also indistinguishable, but they obey the Pauli's exclusion principle. So, they have the integer spin plus half minus half, and you know only plus half can occupy one quantum state, minus half can occupy one quantum state. Although they are indistinguishable, it is not like any number of particles can occupy a quantum state. Okay. So, you have depending on the spin. So, a particle with spin plus half can occupy one particular quantum state, minus half that is the Pauli's exclusion principle. So, now molecules, so these are governed by what is called as Maxwell-Boltzmann distribution. You see Bose-Einstein, Fermi-Dirac, they are all quantum mechanical distributions, whereas the Maxwell-Boltzmann is what is called as classical distribution, because when we are talking about molecules, they are particles essentially, okay, and they are distinguishable unlike phonons, photons or electrons. Okay. So, we will stop here. Tomorrow we will look into some more details of how these distribution functions are represented and so on. Okay. Thank you.